So this is just an introductory session. Today, I will try to discuss the contents that we have in week 1. I hope you have somehow gone through the contents that you have in BUX. Let me show at first which books we have to go through. So first of all, so we all are here for learning Math 215, that is complex variables and Laplace transformations. We can understand that here we have two parts actually, complex variables and Laplace transformations, just like Math 110. In Math 110, you have seen that there is a part differential calculus and also coordinate geometry. In Math 120, you have learned integral calculus and then differential equations. So in Math 215, we have complex variables and Laplace transformations. So invisibly, we have two fields here, that is complex variables and Laplace transformations. But this time, in this semester, we'll try to include another portion from machine learning. For complex variables, we can go through this one. So complex variables by James Brown and Will Churchill. Okay, so this book is very important for the theoretical purpose. If we take a look into this book, you will understand which contents we have in this semester. So chapter 1, 2, 3, 4, 5, 6, and lastly 7. So from chapter 1 to 7 are included in complex variables. Besides this book, you can also take a look into this one, that is complex variables, Strom's outlines. Okay, so this book is very important for the problem solving part. You can easily understand that in this book 640 fully solved problems are here, so this one is also helpful. So if we try to have a look on the contents, just like this book, so here we have chapter 1, 2, 3, 4, 5, 6, and 7. So chapter 1 to 7 are included in the syllabus. So it's up to you. You can go through this book or this one. We need to go through just the theoretical part and mostly some problems. Besides this, you can also take a look into this one, complex variables by Mark Lewis. Okay, so this book is also helpful for problem solving and also for the theoretical purpose. So these three books are for complex variables. And for Laplace transformation, we can go through differential equations written by Danish Gill. From this book, we just need to go through chapter 7. So in chapter 7, you can see that there are some sections 7.1 to up to 7.6. So at least we will try to focus on section 7.1, 7.2, 7.3, and 7.4. But I think 7.1 to 7.3, these are enough. Okay, so this is for Laplace transformations part. And lastly, you can understand that in this semester, we will try to include the portion of machine learning. So for this, you have to go through this book. So Mathematics for Machine Learning, and the author is Mark Peter. So from this book, we need to go through chapter 7. Let me show. Chapter 7, that is continuous optimization, and then linear regression, Chapter 9. And if we get time, then this will be also included, that is PCA, that is Principal Component Analysis. So this is the short overview of this course. Let me start from complex variables. So we can also understand this term as complex analysis. So for this, I have already mentioned that we can go through this book. This is for theoretical purpose, or for problem solving part, Chom's outlines. And chapter 1 to 7, whatever content you have in week 1, that is just going with chapter 1 here. In chapter 1, or let's say week 1, we will learn the basic components of complex number system. Okay, we will learn the fundamental operations, how to represent a complex number graphically, how to find the modulus and argument of a complex number, and also we will try to find the roots of any equation where complex number is involved. And then graphically, how we can represent complex number. So let me start from week 1 contents. Here, first we have to know about complex numbers. And then the fundamental operations. Then we'll try to go through rectangular, polar. That means complex number can be represented as rectangular or also in polar form or in exponential form. We can also think about the trigonometric form of complex number. We'll try to find roots of any equation where complex number is involved. We'll try to learn how to find powers of a complex number. And then we'll try to describe the geometrical interpretation. First of all, let me make you understand what we have in week by week contents. Okay, so in week 1, we will learn about complex number system. In week 2, you will see that just like real valued function, we can also define complex valued function. So in complex valued function, there is a term that is called mapping. So this is important. So you will get this one in week 2. In week 3, so in week 3, you will see complex differentiation. Just like differential calculus, whatever you have learned in Math 110. So here in Math 110, you have learned how to differentiate a real valued function. But in complex variables course, you will learn how to differentiate complex valued function. So in complex differentiation, you will often see that there is a term, namely CR equations. Okay, it is a short form of Cauchy-Riemann equations. In short, I am writing here CR equations. In week 4, you will see some functions where complex number is involved. So that functions may be exponential function, it may be logarithmic function, it may be trigonometric function. We may also have hyperbolic function. In summary, we can say we will learn about elementary functions. Remember, whatever function we are going to learn or we are going to see, all functions obey the property of complex number system. In week 5, you will see the applications of the elementary functions. Same contents will be here. And in week 6, you will learn about complex integration. So in week 3, you have complex differentiation, and in week 6, you have complex integration. So just like math 1 to 0, in math 1 to 0, we have learned how to integrate a real valued function. But here, you will learn about complex valued function and how to integrate complex valued functions. So after week 6, you will get to know power series, or we can say series expansions. So in math 110, you probably have learned about Taylor series, Maclaurin series. So same things will be learned here, but for complex number system. So here you will see about Taylor series, Maclaurin series, and most importantly, you will see about Lorentz series. Our focus will be mainly on Lorentz series. You already have the pre-idea about Taylor series and Maclaurin series, but in week 7, you will see how we can construct Lorentz series. After week 7, you will learn a content that is known as residue. So this term is totally new to you. Besides residue, we will learn about Cauchy's residue theorem. That is, in short, we can say CRT, Cauchy's residue theorem. Just like CR equation, Cauchy-Riemann equation. Actually, Cauchy and Riemann, Augustin Louis Cauchy and Bernhard Riemann, they were the mathematicians. So it is named after them. Okay. So CR, that means Cauchy-Riemann. CRT, Cauchy residue theorem. Within week 9, your complex variables part will be over. That means week 1 to week 8 are designed for complex variables. And then we have Laplace transformations. So Laplace transformations can be found in week 9. Here you will see Laplace transformations, then inverse Laplace transformations, and some applications. So you know that after Laplace transformation, we have another part attached, that is machine learning. So here you will see continuous optimization, discrete models, and then linear regression, and also dimensionality reduction. So in week 10, we will be starting machine learning. These are the tentative schedules. Okay, so I hope you have understood what I have mentioned here. So at this moment, I request you, please try to go through week 1 and week 2 at first. Otherwise, without having the basic concepts, you will have some difficulty in upcoming weeks. So week 1 and week 2 are important. Let me start from week 1. In week 1, we have the contents, complex numbers, how to do the fundamental operations. Operations means summation, subtraction, multiplication, and division. Then we will try to understand how we can convert rectangular to polar. Then we'll try to learn how to find roots of any equation, and then powers of complex numbers, and lastly the geometrical interpretations of some inequalities or equations where complex number is involved. So this is the short overview of week 1 contents. So first of all, have a look on chapter 1 here. You already know what is the real number system. So real number is the largest one. That means we know about natural number set, integer number set. We know about rational and irrational number. And finally, including all these things, we have the real number system. And this is the notation for real number set. So natural number is a subset of integer number. Integer number is a subset of real number. That means real number set seems to be the largest one. But with the invention of complex number system, now we can say that complex number system C, that is the set C, is one of the largest one, which contains natural number, integer number, or real numbers. So the first thing that is coming to our mind, that is, what is complex number? So complex number is denoted as z equal to x plus y I, or we can also denote this one as z equal to a plus bi. So here you can see that we have x component and y component. So x and y are coming from real number set. Similarly, if we write a plus bi, so a comma b are coming from real number set. For example, let's say we have z equal to -1 plus 2i, z equal to 1.5 plus 3 by 2i. It can be z equal to -1 by 2, -3 by 4i. We can also write z equal to √2, -1 over 3i, or let's say √2, +1 over 3i. So these are the examples of complex numbers. So now we can see that the components x and y. So x and y, both of these are coming from real number set. That means these are real numbers. So we have to know what is real number. So real number is 0, 1, 2, 3, -1, -2, -3, up to -infinity, and on right side up to +infinity. So at this moment I have written just integer numbers, but besides this we have also the decimal points. That means let's say it is 1.5, it will be 2.1, we may have √2, √3, -0.5. That means real number set is with all the numbers. Okay, so if we have a look on this example, that is z equal to -1 plus 2i. So here -1 and 2, that is -1 and 2, both are real numbers. But whenever we are writing in this form, -1 plus 2i, it is becoming a complex number. So we have to know what is the standard form of complex number. So the standard form of complex number is z equal to x plus yi, where x and y are coming from real numbers. That means x, y belongs to real number set. So this is the standard form. Suppose we have a number like 2i -1. So this is also a complex number, but this is not in standard form. So sometimes you may be asked to find the standard form of the given complex number. So the same number now we can write as -1 plus 2i. That means having x component first, then y component with I. Okay, so this is the standard form of complex number. Now, the important part is, what is this symbol, I? So here, I stands for imaginary. So square root of -1 is denoted as I. Z equal to -1 plus 2i actually derives from -1 plus 2 root over -1. So whatever notation we have here, it is same as the second one. So square root of -1 is now known as I. So there is a long history behind complex number system. Okay, so we are not going through that one because we'll try to focus on the problem solving parts here. So there are two forms of complex number. Complex numbers can be classified into two categories: rectangular form, and another one is polar form. Already you have seen that.
Sir, are rectangular and Cartesian forms the same one?
Yeah, thank you for your comment. So rectangular form and Cartesian form are the same thing. So these are alternatives. Okay. So rectangular form or Cartesian form, and the second one is polar form. So here we will see how we can write complex number in polar form. So already you know that z equal to x plus yi is the standard form of complex number, but this is called the rectangular form or Cartesian form. But z equal to r e to the power I theta. So r e to the power I theta is known as the polar form. So polar form can be expressed into two ways: in exponential form, and another one is trigonometric form. So that's why I have written earlier here, that is rectangular form, polar form, exponential form, and trigonometric form. So you can see that here we have e power I theta. So e with exponent I theta. So this is the exponential form. And you probably know that e to the power I theta, that is equal to cosine theta plus I sine theta. So you can see that the exponent can be written in terms of trigonometric functions: cosine theta plus I sine theta. So this is called Euler identity. E to the power I theta equal to cosine theta plus I sine theta. So this is known as Euler identity. Leonhard Euler was the mathematician. That's why now it is known as Euler's identity. So using this identity, this number can be written in this way. That is r times e to the power I theta, that is cosine theta plus I sine theta. So we have actually two forms, but we can also say we have actually three forms. That is the rectangular form and the polar form. So polar form can be written in exponential way or in trigonometric ways. Let me write again. Z equal to x plus yi, z equal to r e to the power I theta, z equal to r cosine theta plus I sine theta. So this is the same thing. So remember, the first one is known as rectangular or Cartesian form. This one is the polar form, but specifically it is called the exponential form. And this one is also polar, but it is known as complex number in trigonometric form, having cosine theta and sine theta. So the main theme that we have here, we have to know how we can convert rectangular to polar. That means now we have to know what is r and what is theta. Now we have to know the conversion. But before that, let's try to have a look on the geometrical interpretation of complex number. Let's come from the rectangular one. That is, we have the complex number in rectangular form as z equal to x plus yi. So x plus yi is called the complex number, but remember x and y belongs to real number set. So here x is called the real part of z. Complex number is denoted by the letter z. So x is the real part of z and y. So since y is attached with I, that means y times I, so I is the imaginary unit. That's why y is called the imaginary part of the complex number z. Real part of z is denoted by this notation, Re of z. That means inside the parenthesis we have z. So Re, this is the short form of real part. Imaginary part, in short, we can write Im. So Im of z, that means y. So geometrically, complex number is nothing but a point. Remember, complex number is nothing but a point. That means it is itself a point. So z equal to x plus yi can be thought to be a point x comma y. So this is just a point. Now you know that how we can locate a point in Cartesian coordinate system. So let's say we have the Cartesian coordinate system. It is x-axis and y-axis. But the only difference that we have here the x-axis is called the real axis and y-axis is called the imaginary axis. So whenever you have learned the contents from Math 110, you know that both x-axis and y-axis are denoting the real numbers. But here, y-axis is the imaginary axis. So let's say we have 1, 2, 3, -1, -2, -3. So this is on real axis, that is now known as x-axis. In y-axis, we have I, 2i, 3i, 4i. In downward portion, we have -i, -2i, -3i, and this is going on. So this is the only difference that we have here. The Cartesian system that we are familiar with, that deals with all real numbers, that is 1, 2, 3, -1, -2, -3 on x-axis. On y-axis, we have 1, 2, 3, -1, -2, -3. So you are familiar with this. The only difference that we have here in complex number system, that y-axis is acting as the imaginary axis. So I, 2i, 3i, 4i, this is on y-axis in upward portion, and in downward portion we have -i, -2i, -3i. So writing I every time is an ambiguous process. So that's why what we can do at this moment, we can think that we have just 1, 2, 3, 4. Invisibly, we have I always. So that's why in your reference books, you will see this Cartesian coordinate system. But remember, you are learning complex variables. So y-axis is always acting as the imaginary axis. Okay, so it's no matter we have I or not. So it actually doesn't matter. The thing is, x-axis is the real axis and y-axis is the imaginary axis. So for simplicity, we will use this coordinate system. That means we will not write I. We'll just write the numbers on y-axis. So I hope you have understood this part. So whatever I have told you earlier, that z equal to x plus yi, this is the rectangular form of complex number. So it is nothing but a point. That means it is always representing a point. So you know that if we have to locate 1, 2 point, that means this is x and this is y. So x is 1, y is 2. So on Cartesian coordinate system, we can easily locate 1, 2. So 1 and 2 can be located here. So this is 1, 2 point. Let's say we are targeting for -2, -3. So -1, -2, -1, -2, -3. So the point will be here. This is -2, -3. So we know from the concept of geometry how to locate any point. So complex number z equal to x plus yi always denotes a point. So let's say we have, for example, we have z equal to -1 plus 2i. So -1 plus 2i can also be a point, that is -1, 2. Have a look on the standard form, x plus yi, that is now written as x comma y. So x component and y component with parenthesis. So this is denoting a point. So using this same pattern, I have written -1 plus 2i in this form, -1, 2. That means -1, 2 is a point. So if we want to locate this complex number, -1 plus 2i, So the process is same. Here we have -1, +1, +2. So the point will be here. So the point that we have found is representing a complex number, -1 plus 2i. But since we are learning complex variables, so there is no doubt that it is different from general thinking. Okay, so here we have 1, 2 point, and here we have -1 and comma 2. So the only difference that we have here is that whenever we are locating a point, that should be directed always from origin to that point. That means you can think about vectors. Okay, so complex numbers are acting just like vector. So suppose we have z equal to 1 plus 2i. So this is 1 and this is 2. So this is 1, 2. But remember, don't forget to draw a line that is directed from origin to the main point. So this is the main difference. So whenever we will try to draw any complex number in the plane, that is, here we have x-axis and y-axis, so we have to draw this line. Okay, we have to drag from origin to the point. So the system that we have seen here, that is real axis is x and imaginary axis is y. So it is actually called Argand diagram. That means the diagram that we are having here, that is called the Argand diagram. So mathematician Jean Robert Argand actually used this process to locate any complex number. So now it is easier for us that we can locate any complex number that is in the standard form -1 plus 2i as a point. Let's take one example. 1 plus 2i. 1, 1, 2. So this is 1, 2 point. And we will always draw a line from origin O to the point. Let's say this point is P. So OP will act like a vector. So here you can understand that what is 1? 1 is representing x and 2 is for y. So the distance that we have here, it is 1, and the distance that we have vertically, it is 2. That means if we have a point x comma y, so that point is representing a complex number x plus yi. So the horizontal distance is x and the vertical distance to the point is y. So this distance is now known as real part of z, and the vertical distance y is known as imaginary part of z. So this is the geometrical interpretation of rectangular form. And you know that we have also polar form, that is r e to the power I theta. So now we have to know how we can convert rectangular form to polar form. So now our target is to convert to z equal to r e to the power I theta. So we have the same point x comma y on Argand diagram. That is, we have x-axis and y-axis. X-axis is real and y-axis is imaginary axis. So the distance that we have from origin to the point, you can think about a right angle triangle. That means this is the perpendicular part, this is the base, and this is the hypotenuse. So the distance from origin to the point is a number. So this is r. And the angle from positive x-axis, this is positive x, this is negative x, this is positive y, and the downward part is negative y. So remember, the angle from positive x-axis to the hypotenuse, that is to the line, is theta. So r and theta are the coordinates for polar form, and x and y, x comma y is for rectangular, and r comma theta is for polar. So first thing first is we have to know what is the meaning of r and theta. So in general sense, I have already mentioned that r is the distance from origin to the point, and theta is the angle from positive x-axis to the line that we have directed from origin to the point. So r is the distance from origin to the point, and theta, for now, please try to understand that theta is the angle from positive x-axis to the hypotenuse or to the line. Okay, but we have specific names for r and theta. So the distance from origin to the point is called mathematically modulus. So r is called the modulus and theta is called the argument. So if we have z equal to x plus yi, and if anyhow we can convert x plus yi to r e to the power I theta, so this r is called the modulus and theta is called the argument. So in short, now we can also write r as the modulus of z or absolute value of z. Modulus is the right word. Okay, so modulus of z is now written as r. Argument of z is theta. So for now, here one thing I need to mention, that there is a difference between arg of z and capital arg of z. So you can see that small a and big A, small letter a and capital letter A. So there is a difference. Okay, so we will try to discuss this one later, but for now, remember there is a difference between a small argument of z and capital argument of z. So we have a point xy, and this is modulus r, and this is theta, and also you know that this horizontal distance is x, and this is the vertical distance is y. So remember that this x can also be written as r cosine theta, and this y is r sine theta. That means we can easily generate some formulas from here. So the horizontal component, since we have the angle theta, and the hypotenuse, and also this angle is 90 degree. So this is acting just like a right angle triangle. So easily we can understand that the horizontal distance x can be converted to r cosine theta and y equal to r sine theta. So x equal to r cosine theta and y equal to r sine theta. So suppose we have the polar form, we have r and theta in our hand, then we can easily convert to x and y. But suppose we have x and y, and we need to convert to the polar form. We need r and theta. So how can we find r and theta? We can understand that if this is x and this is y, so from the right angle triangle, you can easily understand that the hypotenuse will be x squared plus y squared. So this is r. We know this is r. So r equal to root over x squared plus y squared. That is modulus of z, that is equal to square root of x squared plus y squared. What about theta? That is from positive x-axis to the line. So the formula for argument of z, now we can understand by theta, it is tan inverse of y over x, or we can say arc tan. That means arc tangent of y over x. That means, in short, we can also say tan inverse y over x. So these are the two formulas that we can apply to find modulus and argument. You all have these ideas already, but since we are the beginners for this course, that's why I am going into details. Okay, so that's why I am taking time. So suppose we have z equal to 1 plus I. So obviously this is in rectangular form or Cartesian form. But from this complex number, if we try to find the modulus, suppose the question is find the modulus and argument. So if we try to find modulus and argument, then what we have to do? We know that modulus is r and argument is theta, and the formula for r is square root of x squared plus y squared. Formula for argument is tan inverse y over x. So here we can see that x is 1, and what about y?
R equal to 1.
Y is also 1. So x is 1 and y is 1. That means 1 squared plus 1 squared. So we have root over 2. If we try to plug in y and x in this formula, so y is 1, x is 1. So tan inverse of 1. So you know that tan inverse of 1 is 45 degree. So theta is 45 degree. So that means initially we have 1 plus I. That means we had 1 plus I. Remember, any complex number is a point. So we can also write as 1, 1. So this is 1 and this is 1. So the point is here, 1, 1. and don't forget to draw a line. Okay, so previously we had the rectangular form, and now using these two formulas we are able to convert to r e to the power I theta. That means now z equal to r e to the power I theta. We know that this is the polar form. So what will be the polar form? R is root over 2 e power I theta, I 45 degree. So whatever meaning we have here, we have the same meaning for here. So z equal to 1 plus I is equivalent to z equal to root over 2 e to the power I 45 degree. So in complex variable, we don't use the degree form. So I suggest you to convert the argument in radian form. So 45 degree is pi by 4. So we can also write root over 2 e to the power I pi over 4. So how can we do the conversion? That is 1 degree is pi over 180 radian. That means 45 degree is 45 times pi over 180. So it is obviously pi over 4. So this is the formula for conversion from degree to radian. So z equal to 1 plus I and z equal to root over 2 e to the power I pi over 4. So now you are clear that this is the rectangular form having x and y components, and this is the polar form having r and theta components. But you know that polar form can be expressed in exponential way and also in trigonometric way. So the form that we have here, that is in exponential form. So the same thing can be written in trigonometric form. So you know that we have the Euler identity e to the power I theta, that is cosine theta plus I sine theta. So using this formula, we can easily write root over 2 cosine pi over 4. That means cosine theta. So our theta is pi over 4 plus I sine pi over 4. So this is another representation of the same complex number. So we have expressed the same number in 3 different ways, but the meaning is same. So now I would like to suggest you that we can easily compute r and theta from these formulas, from these two formulas. But besides having these formulas in our mind, we have to draw, or we have to know the location of the given point, because location of complex number is very important in this course. Okay, so please, whenever you have a complex number, try to figure out where the complex number is located, because this is important. The formula that we have here, tan inverse y over x, so this will sometimes give you some argument that is not going with the actual complex number. So at that portion, what you have to do, you have to correct that argument by adding 180 degree or subtracting from 360 degree, like that. So this is important. Besides using these two formulas, please try to note down the location of that complex number. So now, why location is important? Have a look. So here, the angle that we have found, argument, is found to be 45 degree. So the general definition that I have written here, the argument is known as the angle from positive x-axis to the line. So here we have the positive x-axis. This is the positive x-axis. So the argument will be from positive x-axis to that line. So from our eyesight view, we can easily understand that this angle is nearly about 45 degree, right? Do you agree with my point?
Yes, sir.
Yes, sir.
So this is important. Besides finding the argument using this formula, you have to also check whether it is going with the location or not. Okay. Sometimes you have to correct your argument despite having this formula. So I'm going to that part here. So there are 4 different scenarios in complex number system. So let's say we have 4 points. Z equal to 2 plus 2i, z equal to negative 2 plus 2i, z equal to negative 2, negative 2i, and lastly z equal to positive 2, negative 2i. So I have written here 4 examples. All these are complex numbers because it is going with x plus yi, x plus yi, x plus yi, x plus yi, like that. So here we have negative. So you know that negative can also be thought to be the positive. So negative 2 plus negative 2i. So this is the same notation. So that's why x plus yi is called the standard form of complex number. So the reason behind writing these 4 examples is we have to understand the location of every point. Otherwise, it will be difficult to find the actual argument of the complex number. So whatever I am discussing here, all these things are summarized in BUX. Okay, so location is important. So first tell me, what will be the location of this one? We have total 4 quadrants: first quadrant, second quadrant, third quadrant, and fourth quadrant. Yeah, thank you. It is in first quadrant. So 2 plus 2i can be thought to be a point. So let's say it is 1, 2, 1, 2. So 2, 2. This is here, and always we will direct from the origin to the point. Similarly, for the other 3 examples, so it is negative 2, comma 2. The third one is negative 2, comma negative 2. And the fourth one is 2, comma negative 2. So let's look at the second one, negative 2, comma 2. So negative 2 and positive 2. It will be here, right?
Yes, sir.
So it is in second quadrant. What about the third one? Negative 2, negative 2. So it is in third quadrant. For the fourth one, 1, 2, 1, 2. So this is the fourth point, 2, negative 2. Third point is negative 2, negative 2. So it is no doubt that for all the complex number, the modulus is same. So it is not our target. Our target is to think about the argument theta. If we generally have a look on all the 4 examples, so we will see that for the first one, the angle argument is in between 0 degree and 90 degree, right?
Yes, sir.
We know the definition of argument. Argument is always directed from positive x-axis to the line. This is the white color line, and we have the positive x-axis here. So for the second point, the argument theta can be in between 90 degree and 180 degree. So we are assuming that theta is in between 90 degree to 180 degree. So this is our guess for the third one.
So between 180 and 270?
Yeah, thank you. It is in between 180 and 270. So for the third one, angle lies in between 180 degree to 270 degree. And for the fourth one, always from positive x-axis to the line. We can also come from negative. So since we are the beginners, we will always try to think about the argument. So let's say we have a point here that is on fourth quadrant. So argument will be always directed from positive x-axis to this one. Sometimes we are using these directions also. So both directions are applicable. Argument can take multiple values because we have a difference between small arg and capital ARG. So this is the big difference. So you will learn about this thing later. But for now, depending on the location of a point, we have to think about the argument at first. Let's try to find by using this formula that we know, tan inverse y by x. So we are going for the first one. Here, for the first case, theta will be tan inverse y by x, that is tan inverse y. What is y here? 2. And x is 2. So that means tan inverse 1. So again, tan inverse 1 is 45 degree, that is pi over 4. So, okay. So for now, we are thinking about the degree notation. So for the first case, we have found the angle is 45 degree. So is it going with this pre-assumption? Yes or no?
Yes, sir.
Yes, sir.
That is whatever guess we had previously, that is okay. So that means the angle that is derived from this formula, tan inverse y over x, is correct. Let's think about the second example. So the second example is -2 plus 2i. And with our general view, we can understand that the angle is lying in between 90 degree and 180 degree. So let's try with this formula. So tan inverse y over x. So tan inverse of y. So what is the value of y? Y is 2. And x is -2. So in next step, tan inverse of -1. Is it okay?
Sir, এটা কি somehow plus হয়ে যাবে না? Tan এটা.
So you know one identity that if we have tan of negative theta, so that negative can be pulled out before negative tan theta, right? And the same thing holds for tan inverse. Let's say we have a value here, tan inverse a with negative sign. So that negative can be pulled out before. So here, analytically, we can bring the negative sign before and then we have 1. So we have already done the same thing for the first case, that is 45 degree, right?
Yes, sir.
So don't forget that we have negative sign before 45 degrees. So theta this time is negative 45 degree. But it is not going with our assumption. So the angle that you have found, it is also correct. But
180 plus করব।
yeah, that means the angle that we have found here, negative 45 degree. So negative 45 degree is this one. That means if we extend the line in backward direction, then we are getting negative 45 degree. So our angle is this one. That means the total angle is 180 degree. So just to get this one, the green color angle, so what do we have to do? Total angle is 180 degree. And we need just this one. So we need to add 180 degree with the previous part. Do you understand my point?
Yes, sir.
So it is 135 degree. This part is very important because without having this knowledge, you will not get the difference between small arg and capital ARG. Okay, so since we have found negative 45 degree, so negative 45 degree is this one. That means the line that we have previously, if we extend this one in backward portion, we are getting that it is negative 45 degree. So you know that the total angle is 180 degree. And if we subtract 45 degree, so the remaining angle is 135 degree. So the same thing is going here. Do you understand my point?
Yes, sir.
Okay. Our target is to find only this angle from positive x-axis to the line. That's why we have added 180 degree. So what will be for the third case? So again, the same formula is going to be applied. That is theta equal to tan inverse y over x. So tan inverse of y. So what is the value of y this time?
-2.
-2, and x is -2.
-2.
So let's plug -2 and -2. That means we have tan inverse of positive 1. So you know that tan inverse of 1 is 45 degree. So analytically, we have found the angle is 45 degree. So it is found to be 45 degree. So is it going with the assumption that we have previously?
No, sir.
No. So that means we have 45 degree, that is plus 45 degree. So plus 45 degree. So plus 45 degree is this one. That means if we extend the main line in backward portion, so it is 45 degree. But we need the whole angle. So what we have to do? First tell me what is this one? What is the value of this part?
180
180. So just to get a total angle, we need to add 180 this time. Do you get my point? So theta needs to be corrected. 180 degree plus 45 degree, that is becoming 225 degree. Okay. So 225 degree is going with our assumption. So have you understood what I'm trying to say?
Yes, sir.
Yes, sir.
Yes,
So
sir.
location is important besides using the formula. So if you understand this part, then the whole thing that you have in week 1, that will be easier for you. The contents that we have in week 1, that will be easier.
Sir, what's the difference between capital ARG and
Actually, capital argument, that is the notation that we use, ARG, it is called the principal argument. So it has a specific value. So principal argument generally lies in between minus 180 degree to 180 degree. And it can also be equal to. So capital ARG offset. So this is called principal argument. That means it is a unique value. But the angle that we have here, theta, that is small arg, that can take multiple values. Forget about principal argument now. We will try to discuss this one later. But the main thing is we are learning how to figure out angle of a complex number that is in any quadrant, maybe in first quadrant, second quadrant, third quadrant, or fourth quadrant. Okay, so first, second, third case are over. So let's do it the fourth one. So our assumption says that it is in between negative 270 degree to 360 degree. So let's see what happens. So fourth case. So theta is equal to tan inverse y over x. So tan inverse y. So what is the value of y? Y is negative 2 and x is positive 2. Am I correct? Okay.
Yes, sir.
Okay. So we have negative 1. That means what we can do, it will be negative tan inverse 1. So negative. Now tan inverse 1, you know, it is 45 degree. So the angle that we have found here is negative 45 degree. But the assumption that we have made earlier, we have found negative 45 degree. So this is negative 45. If we come from this part, that means,
plus 360?
yeah, thank you. So we have this point, we are targeting for this angle, but the angle that we have found here, it is in negative direction, so negative 45 degree. So what we have to do, we have to add 360 degree. That means theta should be 360 degree negative 45 degree. So 360 degree negative 45 degree is equal to 315 degree. Have you understood?
Yes, sir.
So that means besides applying the formula, location of the point is important, because the formula is giving us negative 45 degree, but we have to correct the angle based on the location of the point. So this is the short overview of a complex number that can be in any of the quadrant, maybe first quadrant, second quadrant, third quadrant, and fourth quadrant. So now the time is yours. You can think about some problems and try to find the argument based on today's discussion. So we have learned about complex numbers. We have learned the conversions, that is rectangular, polar, and also we are familiar with now the exponential part and trigonometric form of complex numbers. Now we need to know the fundamental operations of complex numbers. So operations can be positive negative multiplication and division. So let's talk about the fundamental operations of complex number system. So the first thing that we have to know about addition, subtraction, multiplication, and division. So suppose we have two complex number. This time I am denoting as Z1 as -1 plus 2i, and say we have another complex number Z2 equal to 1 -3i. So if you are asked to add these two complex numbers, let's say we are going to add Z1 and Z2. So this is addition. So Z1 is -1 plus 2i plus Z2. So Z2 is 1 -3i. So what we can do? -1 plus 2i plus 1 -3i. So addition says us that we have to add the real parts and we have to add the imaginary parts. So -1 plus 1, these are the real parts. So we have grouped these two things, that is -1 plus 1. And the imaginary parts that we have, 2i, -3i. So now it is easy to add. So we have 0 plus, here we are getting -i. So that means it is actually -i. So this is how we can add two complex numbers. So remember, any complex number is a point. So -1 plus 2i is -1 comma 2. 1 comma -3, that is for 1 -3i. So whenever we are adding two complex number, that is also a complex number. So addition is itself a complex number. So that means Z1 plus Z2 is -i. So if we try to write this one in standard form, it will be 0 plus -1i. So that means we have the point 0 comma -1. That means addition of two complex numbers is a complex number. So for now, let me show geometrically. So you will find a pattern. So -1 comma 2. So -1, 1, 2. So this point is representing Z1. 1, -3. 1, -1, -2, -3. So this is Z2. So any complex number can be directed from origin. So that's why we have the first line and also we have the second line. Z1 plus Z2. This is the addition. So if we add Z1 plus Z2, we are getting -i. That means 0, -1. So 0, -1 is here and the line will be like this. So that means this is the addition, Z1 plus Z2. So since it is on the downward vertical axis, so we are directing like this. But the main thing that we have to know here, it will act like a parallelogram. That means, let's take another example. Suppose we have Z1 equal to 1 plus 2i and Z2 equal to -2 or +2i. So if we add these two complex numbers, we will get -1 plus 4i. So it is 1 2 1 1 2, this part, -2 -2 and +2. It will be here. So it is Z1 Z2. I am working with another different problem so that you can easily figure out what is the geometrical interpretation of an addition. So here we are having -1 4. So -1 1 2 3 4. So this is the addition Z1 plus Z2. So that means, let me use another color. So this is the addition. Now the main thing that I want to interpret is that addition is a parallelogram geometrically. So that means we can think about a parallelogram. It is just going with this. Do you understand?
Yes, sir.
Yes, sir.
So every time, whatever complex number you have, that is not a matter, but you have to find a location. We have located Z1, we have located Z2, and also we have located the addition. And geometrically, addition will represent parallelogram. So this is Z2, this is Z1, and the diagonal of the parallelogram is acting like the addition. Okay, so this is the geometrical view of addition. And similarly, we can subtract, we can multiply. But let me show about how we can do the division. So division of two complex numbers. Let's say we have 1 plus 2i and -1, -4i. So we have to divide this number by this number. So this type of division is totally different from real number system. So what we have to do, whenever you will see Z1 by Z2, at that moment, you have to think about the standard form. So what is the standard form? Standard form is Z equal to X plus YI. You can also think about A plus BI. You can also think about capital X plus YI. We can also write like this: real part plus imaginary part with I. So these are the standard form of a complex number. So since we have I here, so what we have to do? So this division can be done by this way. Try to have a look here. So we had -1, -4i. So here comes another part. Another important thing that we have to know about complex conjugate. So what is complex conjugate? Suppose we have a complex number Z equal to X plus YI. Complex conjugate is normally denoted by Z bar. So complex number Z has a conjugate Z bar. In some reference books or textbook, you will see it is written in Z prime notation. So it doesn't matter. Z bar equal to X negative YI. This is the concept that we have for complex conjugate. If we have a complex number X plus YI, its conjugate will be X negative YI. So the change that you have to make is in Y. Suppose you have Z equal to -1 plus 2i. If I ask you, find the conjugate of this number. it will be -1. So x is just same, but y part will be changing. That is, it will be -2y. I hope you have understood.
Sir,
Yeah.
sir, complex conjugate points will be vertically up and above each other.
Yeah. So how it looks like geometrically. So we have -1 plus 2i. So whatever operation you are going to do, all operation has a geometrical meaning in complex number system. So always try to locate the complex numbers in our Gantt diagram. So we have -1 plus 2i. So -1 plus 2i is -1 comma 2 point. So -1, 1, 2. So this is -1 comma 2. So this is our first point, z. And the conjugate that we have found, it is -1, -2i. So -1, -1, -2, it will be here. So it is -1, -2. So you can work with some more examples, but the main thing is complex conjugate z bar is the reflection of the original one. Z bar is the mirror of z, and the vice versa is also correct. Z is the mirror of z bar. Okay, this is the geometry.
Reflection on x-axis.
Reflection on x-axis, or you can say your reflection, or you can say mirror. Okay, or we can say symmetric. We have so many notations, okay, about x-axis. Okay, clear?
Yes, sir.
So our target is to do the division part. So here, what do we have to do? We have numerator and denominator. So the term, the number that we have in denominator, -1 plus 1, -4i, -1, -4i, we have to multiply this with its conjugate, -1 plus 4i. So 1 plus 2i. So just to balance this equation and this one, what we have to do? We have to multiply the same portion in numerator. Okay? And now you have to simplify the denominator, and you can simplify the numerator. Finally, your target is to reach up to a plus bi form. Let me show from here. You can see whenever two complex numbers are in division form, so have a look on the denominator c plus di. So c plus di is written in c minus di. That means this is the conjugate. So these two things are multiplied. And then this is the simple algebra, just like addition, multiplication. So after having this one, you have to reach to the standard form. So how we can reach to the standard form? That is, combine the real part, then make a separation with addition, and write the imaginary part with I. So this is the way how you can do the division. So suppose you have -1 plus 2i by 4. So what you can do? Remember, whenever you are multiplying a complex number with its conjugate, then the denominator will become just a real number like 4. That means in denominator there will be no I. So see, you don't have any I in denominator. Suppose we have this one. So our target is to write it in standard form, so we can easily separate. So that means -1/4, and we can also do some simple algebraic calculation. It is 1/2i. So this is now a plus bi form, x plus yi form. So this is the complex number z. So this thing you have to do here. So now come to the point how we can find roots and powers. And already you have learned what is the geometrical interpretation of complex number, how we can locate a complex number, and what is the interpretation of addition, and what is the interpretation of complex conjugate. Addition is a parallelogram, and complex conjugate is a reflection about x-axis. So we have some other interpretation for subtraction, multiplication with scalar, multiplication with two complex numbers. So these things can be found in your reference books, but I am going through the overall contents. So let's learn about how to find roots of any equation, how to find the power of a complex number. So these two are equivalent. Whenever you have to find roots, automatically you need to find the powers. So how to find roots of an equation. So here, suppose we have a complex number like z cubed, -1, -i. Or let's say positive I equal to 0. So just like algebra that you have learned in your high school level, let's say you have x squared -4 equal to 0. So it will be x squared equal to 4. That means x equal to positive -2. So depending on the degree x power 2, we can understand that how many solutions or roots we have for that equation. So since we have x power 2, number of solutions will be 2. One is +2 and another one is -2. So the same thing holds for complex number system. So here we have z cubed. So how many solutions we will have here?
3.
3. So you are asked to solve this equation, and this equation involves complex number, that is z belongs to complex number system, that is z equal to x plus yi, don't forget. So here you need to follow some steps. Your target is to find z, but for that you have to follow some steps. So step 1, keep z on left hand side of the equation. This is the first step. Step 2, on right side you will have one complex number. So convert the right side complex number from rectangular to polar. That means you need to find r and theta. And remember, whenever you are going to find theta, then argument formula and location is important. After then, you have to apply one formula that is called de Moivre's theorem. So what is de Moivre's theorem? We'll try to discuss later. And finally, we have to make one relation, let's say for zk, not only z, you will have zk. So z sub k. What is the meaning of k? Here the power is 3. So how many solutions you will have for z? You will have 3 solutions. So let's say z1, z2, z3. So that means k equal to 1, 2, 3. But the important thing is don't start with 1. Always start with 0. So if we start from 0, so it will be 0, 1, and 2. That means k equal to 0, 1, and 2. This is the Euler notation. So in step 4, you have to make a relation like zk. So let's try to solve this one. So z cube negative 1 plus I equal to 0. So here, step 1, keep z on left hand side, only z. So if we try to keep z on left hand side, so for now, on right side we have 1 negative I. And our target is to keep just z with power 1. We can do this simple algebra, that is the working rule from exponent. So 3 and 3 can be cancelled. We have now z. So z equal to 1 negative I power 3. So have you understood how we have reached to z? Z
Yes,
equal
sir,
to
understood.
1 negative I power 1 over 3. So convert the right hand side complex number from rectangular to polar. Here I need to include another thing. Convert the right hand side complex number that is in the parenthesis. That should be converted from rectangular to polar. So here we have the inside quantity 1 negative I power 1 by 3. So see, we already have one solution. It is z equal to this one. This is our target. We have the solution. But this is not only the solution. We also have another 2 solutions. So we are looking for that solutions. That's why zk is important. So for that, you have to convert the right hand side complex number that is in the parenthesis from rectangular to polar. So the right hand side complex number that you have, it is let's say it is z1, here denoting like z1. It is 1 negative I. So our target is to convert this rectangular form to polar form. I have already mentioned in step 2. Just to convert this one to polar form, we need to write just like this, r e to the power I theta. So this inside quantity that is in rectangular form should be converted to polar form with power 1 by 3. So now our target is to find r and theta. So r equal to 1 plus negative 1 squared, because here x is 1 and y is negative 1. So this is the thing. So it will be root over 2. What about theta? Theta equal to tan inverse y over x. So tan inverse, what is the value of y? Y is negative 1 and x is positive 1. So that means we have tan inverse of negative 1. That means we have negative 45 degree. So let me write here negative 45 degree. Besides this one, you have to check the location of the point. In which quadrant we have this one?
The fourth quadrant.
It is in fourth quadrant. Yeah, you are correct. That it is in fourth quadrant. So here we can direct with a line. Now the angle will be always from positive x-axis to the line, so we can understand that it is in between 270 degree and 360 degree. So the angle that we have found, it is negative 45 degree. So what we have to do, we have to add 360 degree negative 45 degree. So that means 360 degree negative 45 degree, that is 315 degree. So I have mentioned to you that don't keep degree notation, we can keep it in radian notation. So 1 degree is pi by 180 radian, so 315 degree is 315 pi over 180. So 315 over 180, that will be 7 pi over 4. That means theta is 7 pi over 4. So if you have the calculator, please try to check whether I have written the correct one or not and let me know.
Yes, it is 7/4.
Okay, thank you. So let's count from this one. So we have 1 negative I power 1 by 3. And now we have written this one as r e to the power I theta power 1 by 3. So what is r? R is root over 2. So this is root over 2 e to the power I theta. Theta is 7 pi over 4 power 1 by 3. We are able to convert this into polar form. But here I have mentioned that we have to apply de Moivre's theorem. So de Moivre's theorem says that theta, that is the small argument of z, can take multiple values. So let's say we have this number 1 negative 1. So we can come from positive x-axis to this line. So this is, let's say, theta. If we come by another rotation, so we will get the same line. So theta plus 2 pi. We can come again, theta plus 4 pi. We can come again, theta plus 6 pi, like that. So that's why a small argument can take multiple values, but capital argument is a different thing. It is unique. So we will try to discuss about capital argument later. That is a principal argument. So for now, try to understand that theta plus 2 pi, theta plus 4 pi, theta plus 6 pi. If we go with this way, we will get the same complex number. And also from negative direction, it is true. Suppose we are coming from this direction, we can come from negative 2 pi, we can come from negative 4 pi, we can come from clockwise or anti-clockwise direction. So that's why theta can be theta plus 2k pi. K can be positive or negative numbers. Do you understand my point?
Yes, sir.
If k equal to 1, then 1 rotation is done, theta plus 2 pi. If k is 2, theta plus 4 pi. If k is 3, 3 rotations are done. So theta plus 6 pi, like that. If k is negative 1, so theta negative 2 pi. Here we can write z equal to root over 2 e to the power I. This is our theta. So it can be written as 7 pi by 4 plus 2k pi. That means where you have theta, replace it by theta plus 2k pi. And whenever you are doing this one, you have z to zk. So theta plus 2k pi power 1 over 3. And now you know that if we have a b power m, then we can write a power m b power m. So this identity can be applied. So that is what we can do. Already 80% task is done. So this is, let's say, a and this is b. So a and b. So here we can write root over 2 power 1 by 3 e to the power I 7 pi by 4 to k pi with power 1 by 3. We can also write in multiplication form. How we can write? We can see from here. Let's say 2 power 1 over 3. So you know that if we have e power m power n, that can be written as e power m n. So think about this one. We have e power m power n. So we can write like this way. To the power I 7 pi by 4 plus 2k pi times 1 over 3. So this is so now we can write root over 2 power 1 over 3 e to the power I. We can take the LCM and the LCM is 4. So it is 7 pi plus 2 times 4, 8k pi. So with 1 over 3. So now root over 2 power 1 over 3 e to the power I. And we have 4 times 3, that is 12. So 7 pi plus 8k pi. So finally, we have all the solutions, that is denoted as zk. So here k is our input. We can input k equal to 0, 1, 2, since we have 3 solutions. So you can have a look on the equation. The equation is with z cube. So there will be 3 solutions. And in step 4, I have mentioned that we can input k equal to 0, 1, 2, like that. So if we input k equal to 0, so z0 will be root over 2 power 1 over 3 e to the power I 7 pi plus 8 times 0 pi, so it is 0. So we have 7 pi over 12. And similarly, if we input k equal to 1, so z1, so root over 2 power 1 over 3 e to the power I 7 pi plus 8 times 1, so that is 8. So 8 pi over 12. So 7 pi plus 8 pi, that is 15 pi. So this is our second solution. Similarly, we can find the third one, z2. So root over 2 power 1 over 3 e to the power I. So here input k is 2. So 7 pi plus 2 times 8, that is 16 pi over 12. So we have found all the 3 solutions that we try to find. So for this equation, we have found all the 3 solutions. Now, there is a question in our mind that can't we input 3, 4, 5? That is k equal to 3, k equal to 4, k equal to 5. So the answer is yes, we can input. But the thing is, if we input k equal to 3, we will obviously find z3. But z3 will be the repetition of z0. z4 may be the repetition of the previous z1, and z5 will be the repetition of z2. So that means we can input, but after having the genuine 3 solutions, whatever solutions we will find for other values of k will be the repetition of the previous main 3 solutions. So I hope you have understood. This is the thing that we have in week 1. So thank you for your time. So this is our first session, and we are going to end the session here.
Okay, sir.
So have a good time. Thank you.
Assalamu alaikum,
Thank
sir.
you, sir.